Hello friends, welcome on my channel Jagdish Chaubey. This video is on heat treatment series 2 part 6 on induction hardening. So let's see what it contains. Content. Prior to going in detail, first of all I'll tell you about the flashback. I have already produced heat treatment series 1 wherein there were 8 videos were there on different topics. All these things are mentioned here. Okay. And after that, this current series is heat treatment series 2, wherein I have already produced 5 videos, and this video is on induction hardening. Okay. So next, coverage. What I am going to cover is, first of all, input steel. What kind of steel is used for doing this induction hardening treatment? Generally, this medium carbon steel and carbon steel or low alloy steel, they are also used. But if you want to know in the detail, then you should go for Indian Standard 3930/1994, which says specification for flame and induction hardening steel. So this standard gives all the details about the various steels that can be used for induction hardening. So this you can refer it if you want to know in detail. Then I will cover induction hardening process, then advantages and disadvantages of the process, and finally application. I'll go to next. So first of all, what is the definition? So induction hardening is a surface hardening process wherein steel parts are placed inside a copper coil and then heated above their transformation temperature by applying an alternating current to the coil. Basically, this is a surface hardening process wherein the part is placed in the center of this coil, alternating coil, through which alternating current is passed, and by virtue of this particular part is heated up to above transformation temperature, and then when it is cooled, then it gets hardened. So this is how the definition of induction hardening is there. Okay. Down below is this. I am showing you some of the photographs in one this video shows this induction hardening machine. You can see here is the part is there. Whether the part can move or the inductor can move, there are two different processes which I'll tell you later on. And this is the control panel through which everything is controlled. And this figure is for various types of inductor coil. Whatever is used depending upon the shape of the part or the location of the part where it has to be induction hardened. So accordingly this coil is made, all copper coil is there, and this is a design of this particular inductor is very important in case of induction hardening. Okay. So in the process, there are 4 main components of induction hardening system. One is inductor or coil, okay. Then AC power supply is required. Then part or object for which you want to have induction hardened, and then quenching arrangement. So these are the 4 basic arrangements which are being used in induction hardening system. Process. When a metallic article is placed in a varying magnetic field, eddy current is produced in the part by induction, which is employed to heat the part. This figure A. Same thing when you are placing a part inside this, you see the center of the coil. This is the part and this is the coil or inductor, and this is the power source through which power is supplied, AC current is supplied. Okay. And this current direction is this. And because of this varying magnetic field, okay, it produces a varying magnetic field, and due to this induction process, these parts get heated up because of this eddy current which are produced. Okay. So you see this yellow line, this is the current direction from the power source, and this pink lines are basically eddy current direction. This is the direction and this is this direction. And the magnetic field creation is shown over here. Okay. Now one of the important point is skin effect. What is this skin effect? So in this case, the induced current produces field in the opposite direction of the magnetic field produced by the inductor and thus cancels the effect at the center. Figure B is there. Therefore, the eddy currents are more concentrated at the surface and reduce strength towards center. This phenomenon of eddy current traveling closer to the surface of a conductor or object is called skin effect. Figure C is not here in the next slide. So I'll explain this also. What is this skin effect? When you produce this power you supply to this, again here it is, yellow lines are there, this is a AC current through power supply. This AC current produces varying magnetic field. Okay, this magnetic field is shown. Of the primary is green line is there. Okay, solid line is there, and through this varying magnetic field, eddy current is produced, and the direction is just opposite. So eddy current, you see all pink line going in this direction, and this eddy current also produces a magnetic field, varying magnetic field, which is in just opposite direction to the primary. So if the green, which is primary, is in this, the magnetic field created by the eddy current is this. It is just in opposite direction. So what happens when it travels from surface to core? It gets neutralizes. Okay, here it's all get neutralized, and at the edge or at the surface, it is at the maximum. So in this case, power density or current density is maximum at the surface, and it gets reduced when it travels to center distance. So this particular effect, wherein the skin of the material, that is the surface of the material, is getting heated because of this eddy current, is known as skin effect. Okay, so this is the skin effect. Now I will explain the next slide. It will be more clear to you. See the same figure earlier, it's slightly enlarged. This is the earlier one, which I had shown how this eddy current is produced in different direction, okay, and the magnetic field created by this. Now here also the same thing, but in this magnetic field created by the eddy current, which is produced here, is just in opposite direction. Okay, these dotted lines are in opposite direction, and this is the primary coil magnetic field. Okay, so this is so this produces a opposite direction in the magnetic field, and that is why this magnetic field is at the center is high, and then it reduces. Okay, and thereby the eddy current, which is produced by this varying magnetic field, is also very high at the peak. It is at the peak at the surface, and then slightly it reduces towards the center. This is shown here. It's not very clear, but it's a pink line is here, the eddy current at this particular effect, wherein the eddy current density is much more at the skin compared to the center portion, is shown here in this figure. See, this you can see very clearly. This is the current density, and you see this is maximum at the surface, and slowly it goes down towards the center. This is this x-axis is your depth from the surface. This is the surface, and then it goes below the surface like this. So you see the current density is highest at this particular point at the surface, and then it reduces. So that is why this particular effect is called skin effect. Okay, let's go to next slide. Now I have explained to you about this, how this magnetic field is created and how this eddy current is created and what happens, how it is being heated up. Okay, so now I'll go for this magnetic. Now what are the different induction hardening methods? So this is one method, is static coil or single shot, shown here. In this there are three types of quenching system suitable for small parts having small areas to be hardened, such as head of the bolt. So this is a single shot method, wherein this part is here, okay, and the induction coil is here, okay, the coil is here, and this is power is being supplied, it is getting heated. Then you take out the material manually and quench it in a separate tray or separate rough. Okay, so this is one thing, that manually, or sometime it is dropped also outside this system. After hitting it, you drop it it goes into the tray having water and then it is getting quenched. In the second method, the same thing is there, this part is there and this is heated up, and just below this there is a quenching arrangement is there, and it part this, after giving the proper cycle, this part falls here and goes into the water tray and gets cooled here. In the third quenching system, this is the arrangement for the third system, wherein there is a quenching, the inductor, and within this there is an integrated quenching coil is there. And whenever the cycle is completed, this gets quenched through this quenching coil which is inbuilt into the inductor. So these are the three various methods for conducting this single shot method. Okay. Second method is known as progressive method. In this, again there are two systems. In one system, the part performs two movements simultaneously. As it rotates, it moves along the axis and inductor remains constant. In this particular case, inductor will remain fixed and the part rotates here. See, this rotation is there, as well as it moves on this axis. Okay, so parts moves here and inductor remains fixed here. Then when part comes here, this quenching coil is here and the water is sprayed here around 30 to 45 degree angle. The water is sprayed on the part, and that is how it is getting cooled. So in this case, a separate quenching coil is there. This is a separate quenching coil. In part 2, the part remains stationary and the inductor coil that moves here. Along with that, there is a built-in quenching coil is here. As the cycle is completed, the material is quenched. Okay, so there are these two types of method. One is a separate quenching coil with fixed inductor, and in the second one, it is a integrated quenching coil. Here is integrated quenching coil, but here the inductor moves along the axis. Okay, part rotates like this, but this inductor moves like this and it's get heated, and this is the water quenching arrangement. So these are the two methods, single step and then progressive method. Okay, then I'll move to. Now this slide shows a relation between case depth, power frequency required and surface hardness. In this you can see, if the case depth requirement is 0.8 to 1.5 and the bar dia is 5 to 25, then you need 200 to 400 kilohertz frequency power source. But if you need 1.5 to 3.0 mm case depth, then the bar dia is 10 to 50, then you require 10 to 100. If it is more than 50, then it is 3 to 10 kilohertz. But if the case depth requirement is 3 to 10, it's quite high. Okay, then you require for 20 to 50 millimeter dia 3 to 10 kilohertz. For 50 to 100, it is 1 to 3, and more than 100, it is 1 kilohertz. So this is how the requirement of power frequency, depending upon the part dia and case depth requirement, is shown here. Now in short, I have shown it here also. For low case depth, okay, see, this is a low case depth requirement wherein you are getting a very high frequency, 200 to 400. Okay, it goes like this. But in medium case depth, you require medium frequency machine. In case of high case depth, like this 3 to 10 mm, depending upon the part dia, you can go up to 1 or up to 10 kilohertz. So it is for high case depth, high frequency is lowered. For medium, it is medium, and for lower case depth, frequency is high. Now in this table, I am showing you about the effective case depth in induction hardening. Steel with percentage carbon, varying percentage carbon, and this is HV, hardness in VPN scale, then hardness in Rockwell C, and hardness in Rockwell A. This I am showing you because whenever you have to measure effective case hardness, you have to decide a cutoff point of hardness. At what particular cutoff point you take the case depth measurement, and that varies from percentage carbon. See here, 0.28 to 0.32 carbon is there. Then the hardness cutoff point is 350. If it is in HRC, it is 35. HR, it is 68. Similarly, 0.3 to 0.42, it is 400 here. It is 40 here. It is 70. And if it is more than 0.53 carbon, then the cutoff point for checking the case depth is 500. HV, 50 HRC and 76 RC. In this case, one more thing is to be taken care is that if the case depth is low, then you should measure only in HRA. But if the case depth is medium or high, then you should go for HRC measurement. This precaution you have to take. Okay. And for this, if you want to refer about this, you can refer IS 6416-9088, which gives about the how case depth has to be measured and what are the cut-off points. Okay. So now I'll move. Factors which are influencing quality in induction hardening. The foremost parameter is proper design of the coil and inductor. This is the utmost requirement, that whatever coil you are designing, it has to be proper as per the shape requirement, as per the location requirement. Okay. So this is the most important point in case of induction hardening, that a proper design inductor is required. Okay. Second point is proper selection of machine frequency based on the case depth requirement. This I have already explained in my previous slide, that based on the case depth requirement, you have to select a proper frequency power source, okay, as per the requirement of the case depth. Then proper design and placement of separate and integrated quenching coil. Wherever you are using separate or quenching coil, integrated quenching coil, their placement must be properly designed, where to place, because it travels and at particular time the part has to be quenched. So where it is to be placed, this has to be decided very carefully. Okay. Then the quality of quenching medium, that is water or oil. This is also very necessary. What is the quality of water? Generally they are using DM water in this case. And in case of oil, you should go for a high flash point oil, because whenever the part is heated and it is quenched, if it is nearby, then it may catch fire also. So you have to select a proper oil also for this particular induction hardening system. Then the other point is sufficient quenchant flow must be maintained to cool the part. See, the basic thing is that the part has to be cooled at a very high speed. Okay, then only you can get martensitic structure on the surface. So for that, quenching flow, whatever quenchant is flowing, whether water or oil, it has to be sufficient and very fast also. So that is a prime requirement again. Then adequate ventilation for removal of oil fumes in case of oil quenchant. In case of oil or even water also, whenever you do it, fumes are produced, whether it is oil fumes or it is vapors are there from water also. So there has to be a proper ventilation around the machine where this particular thing is being conducted. Okay, this arrangement has to be made. This is a very precautionary measure. Otherwise, because of oil, if it is less flash point oil, then it may catch fire also. So this precaution has to be taken, that there has to be proper ventilation. And the last one is improper quenching may result into a soft spot or quenching crack. So if the quenching is not proper, whether the location is not proper of the quenching coil, or the water flow or quenchant flow is not proper, or the speed is not proper, in that particular case, it can produce a soft spot or even quench cracks also. So all these parameters are there which are affecting your induction hardening quality. Either it is a surface hardness or case microstructure or case depth. You have to take care of this. So these are very factor influencing quality, as well as they are a precautionary measure also. Okay. So let's move further. Advantages and disadvantages. First point is high production due to less heating time because of rapid heating. So it is because you are heating at a very faster rate, therefore the heating time is very less, and then you get the same case depth in a very short time. That is why the production is quite high. So it's a quietly productive system or induction system wherein you can produce number of components using a very small time as compared to carburizing or any other process. No surface decarb or deoxidation. There is no surface decarb is there, and there is no oxidation, because the part is exposed to a very small time. Okay, it is in terms of seconds. So it is not getting exposed to air or other thing. So there is no chance of any oxidation or decarburization. Okay, so no surface decarb or oxidation. Then the third point is high hardness up to 55 to 65 HRC can be achieved depending upon steel composition. Yes, it varies from the composition to composition, but you can achieve up to 55 to 65. It's a quite good surface hardness. Okay. Then case depth point. Case depth can be accurately controlled. If the process parameters are controlled properly, then you can control the case depth also. Okay. Then operating cost per part is less. Yes, because the heating time is quite low. Okay, then you can have number of components in a particular time, and the current or power consumption will be comparatively, compared to the production, it will be less. So that way it is economical also. Okay. High wear resistance and fatigue strength. This is a common point for all parts which are surface hardened. Okay, they give a very high wear resistance and fatigue strength. Okay, and the last one is can be automated for similar parts. If you have huge requirement of same parts, then the most economical process will be induction hardening, because it can be automated also. If the process parameters are controlled, they are confirmed, specified, and you maintain that, then you can automate also. It can go for automation also. So these are the various advantages of this process. And the disadvantages: initial high capital investment is there, machine is quite costly also, and the other managements are also quite costly. So initial investment is quite high. Then the second disadvantage is for each part you have to make separate coil. Okay, and all these coils are also quite costly. So for each part you have to make separate coil. This is also a disadvantage. Then highly skilled operators required to control the process. Since the process parameters are very critical, you need to have a good skilled operator to control all those parameters. Okay. Then only limited type of steels can be induction hardening. You cannot harden everything. Okay. And the last one is material limitation. Same thing. Means you can't go for a low carbon steel for induction hardening. You have to have a medium carbon steel, and then you can go for a alloy steel also. So there is a material limitation also. Okay. Applications. You can go for all these automotive parts like crankshaft, axle shaft, spline shaft, universal joints, then gears, cam lobes. Cam lobes are also induction hardened. Okay. Shafts, stampings, spindles, studs, lathe beds. Okay. Lathe machine beds are also induction hardened, but it requires a very high surface hardness for a proper wear resistance. Okay. Then transmission gears are also. All these things are parts which are getting rotated or working on something, so it needs a very high wear resistance and surface hardness. So for that you have to go for a induction hardening system. Similarly, rolling mill rolls, they are also a high surface hardness as well as case depth is also required. Okay, the rolls are rubbing against each other, so it requires a very high wear resistance also. Then pliers and hammers. So all these are parts which can go for induction hardening. Okay. So as far as this induction hardening system is concerned, I have already completed this, wherein I have covered induction hardening. First of all, the definition of induction hardening, then types of machines which are required, then what are the different types of inductor coil, then about the technique of producing this eddy current, magnetic field control and all those things, and skin effect also I have explained separately. And after that we have gone for a different induction hardening methods. It's a single shot or fixed coil, and in other case it is a progressive method. So all these things were explained, and after that I showed you various precautions or various factors which can be taken care during induction hardening, or what are the factors which are influencing your induction hardening system. So that also I have explained, and previous to that this is advantages and disadvantages of induction hardening, and lastly this applications. So I hope this induction hardening system, whatever I explained to you, it will be very useful to you. I have tried to cover most of the important points for this induction hardening, and I hope that you will take advantage of this particular presentation. If you have liked this, then kindly like, and you can give your suggestion also, share with your friends, and if you are new to my channel, then you can subscribe also my channel. So I think I have explained most of the things about this induction hardening. The next part will be coming on part 7, that is on flame hardening. Okay, HT-2 part 7 on flame hardening. So this I will go for next presentation for flame hardening. I hope you must have liked it. If you have liked, then please like also on my channel. Comment also, give your comments, share with your friends, and if you are new on my channel, then kindly subscribe also. Thank you very much.